General relativity describes gravity as the geometric curvature of a smooth, continuous spacetime manifold. Quantum field theory dictates matter manifests as violently discrete, probabilistic quanta. Despite a century of sustained theoretical effort, welding Einstein's deterministic geometry to Planck's discrete mechanics remains unresolved. Modern fundamental physics often handles this by substituting verifiable experimental validation with the mathematical elegance of structural formalism. Standard quantum field theory bridges this divide using conditional wrappers. Theorists mathematically paste continuous geometry over discrete topological axioms and then introduce ad hoc regularizers, like ghost fields, to hide the infinite redundancies those continuous assumptions create. To bridge the continuum-discrete divide without epistemic compromise, these conditional assumptions must be excised. We must either derive the space-time architecture natively from the underlying topological axioms or remain conceptually gridlocked. The theory of infinity, or TOI, introduces a structurally distinct mathematical alternative. It bypasses the standard atomistic premise, aiming to bridge the divide through a strictly native mathematical derivation. We will trace this proof directly. It begins with a discrete topological root, builds a covariant state bundle natively, and mathematically eliminates continuous gauge ambiguity without relying on manual subtractions or ghost fields. This rigorous differential geometry concludes with a highly specific, falsifiable prediction: a 1.738% topological suppression in the Thomson scattering cross-section. If this mathematical proof holds, it provides an exact, measurable fingerprint of the universe's discrete topological boundary physically interacting with continuous space. The mathematical bridge connecting the discrete topological substrate to continuous gauge physics is established via the Sinc-Gauge equation family. We interrogate the symmetric sector first, sinc of x plus the square root of 1 minus x squared, evaluating it to look for any continuous, non-zero real propagating roots. The absolute value of the real sinc function cannot exceed 1, while the absolute value of the derived root requires it to be greater. Algebraically, the curve is mathematically forbidden from crossing the zero line for any non-zero coordinate. The continuous extension forces the root strictly to the zero-dimensional point at x equals 0. This is the theorem of symmetric removable closure collapse. Because this sector yields exactly 0 propagating moduli, the foundational vacuum state is structurally protected. It's absolutely stable, devoid of spontaneous propagating symmetric anomalies. The emergence of physical reality hinges entirely on finding a propagating root. This forces us into the asymmetric sector, sinc of x minus the square root of 1 minus x squared. By interrogating the first and second derivatives, the algebraic bounding logic proves the function is strictly concave across this specific isolated interval. Evaluating the boundaries reveals an undeniable sign change. Combined with the proof of structural concavity, this guarantees exactly one single unique real root crossing the zero axis. With the symmetric field permanently closed off, this highly precise asymmetric modulus acts as the exclusive geometric seed for all propagating physical moduli. We map this propagating modulus to a photon using Wigner's little group classification. Massless particles cannot be brought to a rest frame. They possess unphysical translational degrees of freedom that generate infinite continuous gauge redundancies. Conventional physics handles these translational ghosts post hoc. Indefinite metric spaces, or Faddeev-Popov ghosts, are manually introduced to cancel out the resulting longitudinal states. The TOI framework operates under the friction versus fiction protocol, rejecting manual mathematical subtraction. Continuous fictions must be resolved by the native topological friction of underlying boundaries. The symmetric removable closure collapse derived a moment ago maps exactly to the kernel of the little group action, acting as a golden boundary clamp over the translational axes. Because the continuous field extension permits no symmetric roots, the translation generators are mathematically starved of the spatial volume required to manifest. They are natively annihilated by the topology itself, reducing the little group strictly to the pure rotational subgroup. absolute gauge invariance is achieved natively. Longitudinal states are simply forbidden from existing within the topology. With the translation generators annihilated, the framework must rigorously derive the genuine quantum spin representation for the photon packet. The asymmetric branch generates exactly one one-dimensional transverse line, inherently forcing exactly two mathematical orientations. The framework formalizes this binary label as the parity pulse. By complexifying this real two-dimensional transverse span, the discrete parity pulse maps exactly onto the continuous chiral eigentates of the surviving spatial rotation. This complexification reveals photon spin as the exact native topological generator translated into a continuous observable. Pushing this discrete topological boundary through the continuous vacuum creates measurable friction. Standard QED integrates over 4 degrees of freedom, but TOI dictates the photon drags its fractional root, dilating phase space. Subtracting baseline 4 from the spectral parameter isolates the residual discriminant at 0.03476. This residual discriminant is the unavoidable phase space deformation. It represents the unyielding cost of forcing a discrete geometry to operate inside a continuous universe. We measure this phase space deformation directly against physical phenomena, specifically focusing on the low energy limit of elastic photon-electron interaction, Thomson scattering. In standard perturbation theory, the total scattering cross-section is derived by integrating the matrix amplitude over the invariant Lorentz phase space. The expected value is directly proportional to the square of the available continuous density of states. Because TOI phase space is mathematically dilated, the available continuous volume is natively suppressed by the topological drag ratio. Integrating the residual discriminant modifies the classical expectation, generating a falsifiable prediction, exactly a 1.738% suppression in the Thomson scattering cross-section. These historical anomalies in QED scattering data represent the literal, observable fingerprint of a native, discrete topology pushing through our continuous reality.